I showed you how to solve Hess's law problems using what I call puzzle pieces. But you'll notice that in this problem here, you're not given any reactions underneath. And the problem says, given a table of triangle HFZ, what the heck is that? So we're going to start right here, and we're going to try and figure out what this code means and how to solve this problem using the code. So what the heck is that, and how do we interpret it? So here we go. We're going to look. Triangle means that we are going to be taking a difference. So let's do this. We're going to be taking a difference, and our differences are always our final minus our initial, or our ending minus our beginning. It's always what triangle means. H, as you should know by now, is our enthalpy. F means that this is going to be a specific enthalpy. It is our enthalpy of formation. Now, an enthalpy of formation means that we will be constructing things out of elements. So everything is going to be made out of elements, not out of compounds like we did before. So in the puzzle piece ones, a lot of those things were like, hey, we make a compound or compounds make compounds. But in this problem, we are specifically looking at how do you construct things out of their elements. The last piece of code here is that 0 on the top, which means standard conditions. And standard conditions, temperature and pressure, it's going to be room temperature, which is about 25 degrees Celsius, and standard temperature is, or standard pressure, sorry, is 1 atmosphere. You don't need to memorize this. Usually it's written in the tables, but standard conditions are going to change throughout the year. When we're doing thermodynamics, we'll be looking at room conditions like normal room temperature of 25 degrees C and normal room pressure. But when we're doing things with gas laws, standard temperature and pressure are different. So you need to keep in mind just what are my standard conditions. So again, we're going to subtract our enthalpies from the end minus the beginning, and they are specific enthalpies in this problem that are things made out of elements. Okay, so let's go back to our problem. So where are we going to find these amazing delta H values? They are going to be in this table that I provided for you. You actually have a copy of it on Schoology. But before we can get there, we kind of need to know what we need to know. So I'm going to tell you to come over here and write down the things that you have. O2 gas and zinc sulfate. Now, it's important that you write down the states: solid, gas, gas, solid, solid, gas, gas, solid, because when we look them up in the table, they are listed by what form they're in, what state they're in, and they are listed alphabetically. So aluminum comes first, then barium, and so on. The thing is that they are listed alphabetically by their name. So you would find iron under I, not under Fe. Let's go to the end and pick up our zincs. So zinc sulfur, or zinc solid, sorry, is 0. So I'm going to record 0. Zinc sulfate is negative 983. And oxygen over here is also 0. Wait a minute. Why am I getting zeros? What do these have in common? Well, they're both elements in their natural state. Zinc comes as a solid. Oxygen comes as a gas at normal, like room temperatures. So what the table's trying to tell you is it doesn't take any energy to form oxygen element as an element, because that's how oxygen comes. It doesn't take any energy to form zinc as a solid at room temperature, because that's how zinc naturally is. It just sits there. So now our only last thing is to look up the sulfur. So let's scroll up a little bit here and find the sulfur. Here we have sulfur. If it were rhombic or monoclinic, whatever those mean, that would be what is considered to be sulfur's natural state. But we have S8 as a gas, which means that we are talking about 102 kilojoules, and it's positive this time. We got negative for zinc sulfate, and sulfur 8 gas is positive. Okay, so now we're going to return to the problem, and we are trying to find a delta H, which means we're going to take our end minus our beginning. So the way you're going to see this written on your formula sheet is that we'll take all of our products and we're going to add all of our products together. So that's our end. In this case, we only have one product. And we're going to subtract all of our, oops, that's a really weird sigma there, all of our H's for our reactants. And that's going to give us our delta H of reaction. Okay, so if we take all of our products minus all of our reactants, we get the delta H of reaction. So we take our delta H for our product, which is negative 983, and I'm just going to throw some brackets around that. And I'm going to subtract all of my reactants. So zinc was 0, sulfur was was 102, positive 102, but I only need an eighth of it. So I'm going to take an eighth, because remember our rules, if we multiply something, we need to do it to both the reaction and the heat. So this is going to be an eighth of 102 and 0. Okay, so we wind up getting 983 minus an eighth of 102 is 12.75. I'm going to round that to 12.8. So we've got 12.8 here, or basically 13. And so that becomes negative 996 kilojoules per mole of reaction. So this reaction here will release negative 996. I know it releases because it's a negative sign, meaning it's exothermic. Notice that my answer of negative 996 was really close to the heat of formation of zinc sulfate. So this means this number right here was if we built zinc sulfate out of its elements. So if we took zinc, sulfur, and oxygen and built it strictly from elements, it would have released 983 joules. But remember, I said that the sulfur in its S8 form was not quite the lowest elemental form. And so in this case, this is not a heat of formation because one of our elements, quote unquote elements, is not in its simplest form. Let's do one more example of this. So let's say I've got oops, what did I do there? Let's undo that. Okay, so sorry about that. Here we go. All right, so here we have another one of these crazy reactions where we're told to use our table of delta H values. So in order to get there, let's copy down what we're going to need. That way we don't spend a lot of time scrambling around. So we're going to need C2H2 as a gas. We are going to need oxygen as a gas. We're going to need carbon dioxide as a gas. And we are going to need water as a vapor. Now, water as a vapor, why isn't it called gas? Because gases, that term is reserved for things that are gases at room temperature. At room temperature, water is usually a liquid, and so we talk about water vapor because it's not usually a gas at room temperature. All right, let's look them up. So we'll start with the carbons at the top here. We need C2H2 as a gas, and that is 227. So positive 227. Carbon dioxide is right up here. That's negative 393.5. And water down here as a gas is negative 242. And I'm not even going to go bother to find oxygen because I remember from the last problem that it is an element, and all elements in their natural state have zero heat of formation. So let's look. Here you have cadmium, 0. You have carbon, 0. Chromium, 0. Copper, 0. Any element in its natural state at room temperature has no heat of formation. All right, let's get back to the problem. We're going to do our products minus our reactants. So we had a product of carbon dioxide, and we had 2 of them. So I'm going to do 2 times negative 393.5, and I'm going to add my negative 242. There are all my products, and I'm going to subtract my reactants. My reactants are 227 and 5 halves of 0. 5 halves of 0 is just 0. So when I take 393.5 and multiply by 2, I get 787 minus 242 minus 227. And if I put all those things together, I get negative 1256 kilojoules per mole, or kilojoules per mole of reaction. Now, this thing is nowhere near heat of formation because I've got a compound forming compounds. And I've got a compound forming multiple compounds, which is also not a heat of formation. A heat of formation would make 1 compound. All right, we're done with our examples, but I wanted to point out one more thing from the table, which is I want to take a quick look at our C2H2 and the C2H4. So this table, remember, is a heat of formation table. So if I wanted to make C2H4, I would need to take elements of carbon and elements of hydrogen, and I would bond them together. And the table tells me that this would be 52 kilojoules. Notice that it's positive because I have to release the energy. Okay, now something's wrong with my diagram here. My carbon is actually missing a bond. So a double bond will release 52 kilojoules of energy. Now let's do the same thing for C2H2. So C, C, and 2 H's. If I fill in my bonds here, this is going to be a triple bond. And the triple bond is going to release 227 joules of energy. And so that's 227. And here's why people say, wow, bonds, the stronger a bond is, the more energy it stores. Because look, a double bond would, quote, store 52 kilojoules, where a triple bond stores 227. But that is a lie. You need to be super careful. It's not storing it. This is positive. So it's actually releasing this energy. So a triple bond actually releases more energy than a double bond does. So I'm always careful with the term like to store the energy in the bond, because when you make a bond, it is always energy releasing. Okay, good luck with the Hess's Law problems. Now that you've seen both types, you know that you should be either using some kind of table or set of reactions to solve them. Good luck.